What I'm actually going to do is open this up in the Google Classroom app, because when I open it in the Google Classroom app, remember, I get this option that I can actually write directly on the document. And the way that I'm going to do that is by clicking on this pencil icon in the top right. Okay, so now that it's opened up in this new screen, I have the pen tools available to me down here at the bottom. I can choose the color and the pen size and whatever I might want to use, and write directly on here before I turn it in. So anyway, let's get started. This first question has to do with similar triangles. Actually, this whole lesson has to do with similar triangles, specifically similar right triangles, because it kind of follows directly from our similarity unit into this trigonometry unit. All right, so what we're going to do here to start is we're going to take a look at these two similar triangles. They told us that the triangles are similar, and we're going to use the ratio of sides of the known triangle to figure out what the ratio of the unknown triangle sides would be. Because remember, all sides change proportionally in similar triangles. So the ratios of the sides would be the same. All right, so if I'm looking at part A has LM to LN. LM is the bottom, and LN is the hypotenuse. So the ratio of those sides in the unknown triangle is the same as the ratio of the sides in the known triangle, and it's 12 over 13. All right, now we want that as a decimal, so I'll open up my calculator here. 12 divided by 13 is 0.923, so nearest hundredth would be 0.092, or 0.92. All right, now the next one, MN to LM, MN is the short side here, and LM is the bottom side here, so 5 over 12. All right, I'll go over to my calculator again. 5 divided by 12 is 0.4, what was that? 0.42 if I round it. And the last one looks like MN to LN, which is the short side to the long side, so 5 to 13. All right, finish it off with the calculator. 5 divided by 13 is 0.38, so equals 0.38. All right, so the first one's done. Now, those ratios of the sides are important, remember, because the ratio of the sides is actually going to be a big part of the trigonometry unit that we're getting ourselves into here. Okay, so for number 2, again, more similar triangles. These triangles we don't actually have pictures of, so the first thing you're going to do in a question like this is draw the triangles. And it doesn't necessarily matter how they look. What matters is how we actually label them. So my first one's going to be like that. My second one going to be like that. We're going to assume that I drew them similar to each other, even though they're not quite. The first one I'm going to call R, S, T in that order, which means the next one needs to be W, X, Y in the same order. Let's make that look more like an X. Now, I'll label the sides. RS is 18. We'll zoom in a little bit. RS is 18. ST is 25. And TR is 11. Following the pattern from the first question, the closest to the ratio of XY to WX, that's this side to this side, it would be 25 over 18. Well, what's 25 over 18 equal to? Go back to my calculator. 25 divided by 18 is 1.388. Well, let's see, that's definitely choice 2. All right, 1.388 is choice 2. Moving on, number 3, similar kind of question. All right, so we have 2 similar triangles, but no picture. Let's draw them. Here's the first one, M, N, P. Here's the second one, make it a little bigger, Q, R, S. Okay, so MN, that's 14. NP, that's 8. And MP is 16. And then we know that QS is 7. So it looks like I drew the small triangle and the big triangle backwards, but that's okay because it doesn't necessarily have to be to scale. What we're going to do now is we're going to choose which of the following equations could be used to find the length of QR, this unknown side. So remember, I got to pick corresponding sides and group them together. One of my answers that may or may not be an answer choice, for example, could be 14 over 16 equals X over 7. Right? But since I don't see that one on here, we got to find a different one that matches that sort of pattern. 7 over QR, let's see, 7 over X equals 16 over 8. That one's no good. Let's try number 2, QR over 14. Those correspond, so that's a good start, equals 7 over 8. Those do not. So choice 2 is out. 3, 7 over 14. So 7 over 14, those don't correspond with each other. I'm going to stop right there. It actually must be 4. But just to finish it off, QR, that's this side, over 7, which is this side, equals 14 over 16. Now we're matched. All right, so that one's done. Number 4, Justin is 74 inches tall and casts a shadow that is 102 inches long. When you have a question with a shadow like this, draw yourself a picture. All right, so it looks like we have a person and we have a tree. So here's going to be my tree. Try to make it a little bit straighter, close enough. And here's my tree shadow. Then we have a person over here. And then we have the person shadow. All right, now both of these two pictures form right triangles. And these two right triangles are similar because the shadow, the tip of the shadow to the top of the tree and the tip of the shadow to the top of the person is going to make the same angle with the sun up there, wherever it is. All right, so hopefully that doesn't mess up question 3. But since we have a right angle and we have a similar acute angle down there at the bottom right, those two triangles must be similar. And since the triangles are similar, we know all sides are proportional to each other. All right, so let's label what we know. Justin is 74 inches tall and casts a shadow that is 102 inches long. At the same time, a tree casts a shadow that is 39 feet long. And we want to know how tall it is. Now, you probably noticed something here, or at least I hope you did. Justin and his shadow are labeled in inches, and the tree and its shadow are labeled in feet. All right, so I'm going to put, to signify a single apostrophe for feet, I'm going to put a double apostrophe for inches. Now, what you'll notice in this question is, since both parts of the person shadow are inches and both parts of the tree are feet, we can actually just leave it and solve as is. The next question, we won't be able to do that anymore. All right, as long as units are consistent in one triangle or in each triangle, this is okay. But if the units are different inside the triangle, we'd have to do some conversions. In this one, no conversions, just a simple ratio. So something like X over 39 equals 74 over 102. Okay, so we're going to cross multiply. The right-hand side, I'm going to write 102x. On the left-hand side, it's 74 times 39. Let's see. 74 times 39, 2886. All right, so divide by 102, and we're going to get x is equal to 2886 divided by 102. Looks like 28.29 feet. Now it says to the nearest foot, right? So 28.29 feet, that's just 29 feet. All All right, and I'll make sure I include units in the answer, just like you got to do in Algebra 1. Next. Okay, so now, like I said, number 5, we have, again, similar triangles. We have kind of a weird situation where Katie's being unlucky, I suppose, and standing underneath the ladder. But Katie makes a triangle, and the ladder makes a triangle. And both of these are right triangles, and both of these are similar to each other. All right, so I'm not going to redraw it. I think we have enough visualization here that we don't really need to do much, but I will point something out to you. This blue triangle, the triangle formed by Katie standing under the ladder, is inches on the bottom and feet for the height. All right, we have to make sure we're using the same units for the same triangle. Okay, really with a question like this, we should try to use all the same units, but as long as one fraction has one unit and the other fraction has the other unit, everything should work out. All right, in any case, if I want to convert 5 foot 6 inches to inches, I'm going to take 5, the number of feet, times the number of inches in a foot, and add the number of extra inches. Well, 5 times 12, that's 60, plus 6, that's 66. Okay, so Katie is 66 inches tall. That means instead of using 5 foot 6, I can use 66 inches. All right, now my ratio may be something like 16 over 66 equals 4.5 over, and again, what are we looking for? We're looking for how high the ladder reaches up the wall. I'm going to call that distance x over there. So 4.5 over x is my right side of the equation. All right, I'm going to cross multiply. I'm sort of out of room, but we'll make it work. This is going to be 16x. The other side is going to be 4.5 times 66. 4.5 times 66 equals 297. All right, 297 divided by 16 will give me my answer. So 297 divided by 16 equals 18.56. All right, so there's our answer. What's the unit for our answer? Well, remember, the entire right-hand side, the ladder plus the height, is going to be in feet, and we're looking for the answer in the nearest tenth of a foot. So what tenth of a foot? That's one place after the decimal, which means my answer is 18.6 feet. All right. What might be some factors now that we can say would cause error in the estimate for problem 6? Because this is an estimate after all. List as many as you can. You might be able to come up with a couple strange ones. There's probably an infinite number of weird, strange answers that we can use. For example, the person's height isn't exactly 5 foot 6, right? Or it's not exactly 16 inches. But I think the biggest one here is if Katie wasn't standing straight, these wouldn't be similar right triangles. Right? If she had a little bend at her waist or she was leaning over a little bit. So similar triangles are what makes the ratios accurate. So let's just say that. Let's say person not standing straight. All right, because I think that's the biggest one that would cause error. Anyway, moving on. Number 7, last one. The line drawn on a coordinate plane here to the right, it has points A, B, and C with the coordinates given. Right triangles are drawn using D and E. First, segments AD and BE are parallel because they're both horizontal. What does this tell you about angle BAD and angle CBE? Well, remember, there are parallel lines cut by that transversal. When we have parallel lines cut by a transversal, we can look for a couple different things like alternate interior angles, or in this case, what I would consider this angle and this angle here, especially if I were to maybe extend this line a little bit, is they are corresponding. So what we can do is we can say they are congruent corresponding angles. All right, so they are congruent corresponding angles. I don't like that. I'm going to rewrite that a little neater maybe, or try. Congruent corresponding angles. Okay, now again, I want to point something out to you because a lot of people sort of skip over this when we do angles a lot, and I just did too. Angle BAD, remember, to get angle BAD, we're going from B to A to D. That's our angle. To get angle CBE, let's do that in red. We're going from C to B to E. That's our angle. Those two angles are corresponding with one another. They're both on the same side. They're both on the top of the parallel of each respective parallel line. So we call those corresponding angles, and they are congruent because corresponding angles are congruent when formed by parallel lines. Okay, so why must BAD be similar to CBE? So remember, BAD is that small triangle over here, and CBE is the bigger triangle over here. Why are they similar to each other? Well, we have a couple of different ways to say triangles are similar. The one we use most often is angle-angle. And the thing to remember here is, of course, that's a right angle. And of course, this is a right angle. Therefore, we have angle-angle similarity. So let's write it A similarity. All right, so part C, find the slope of AB and BC below. Show your slope calculations. Okay, AB and BC. What do you notice about those two lines? Hopefully, you notice that AB and BC are technically the same line, and we have to happen to have the same exact slope for both parts of those. Let's calculate it by just counting. It says slow your slope calculations, but I'll show my slope calculations by counting on the graph. And when we do something like that, as long as we're sure that we're hitting points and not just estimating that we hit points, we can show that on the graph. So from A to B, I go up 2 over 3. And if I keep going up 2 over 3, up 2 over 3, up 2 over 3, I know that I found the slope not just of AB, but also of BC. All right, so I went up 2 over 3. Remember, slope is always rise over run, or change in y over change in x. So let's do rise over run equals 2 over 3. All right, and I'll write it for both. No work's really necessary if you can show on the graph that you counted with something like the steps that I drew in there. Okay, so slope is always rise over run. Slope is always figured out from left to right. All right, never forget that. Rise over run from left to right. Giving your answer to B, why does it now make sense that the two slopes in C are equal? Well, there's a couple of different ways that we can write this answer. Number one, it's the same line. Okay, that's not the answer that we're going for in this question, but that is an answer. The answer that we're going for here is that since these triangles are similar to each other, that means there's a similarity transformation that maps one to the next. And if there's a similarity transformation that maps one to the next, we remember that similar or similarity transformations like dilations preserve angle measure. All right, so let's just write it like that and we'll call this lesson over. Why does it make sense they're equal? Since triangles are similar. And similarity transformations preserve angles or angle measure. The slopes must be the same. All right, so that's it for this. Any questions, let me know. I am also posting for today another Google form or another document I want you to turn in. I think it's going to be a Google form. In any case, that's actually going to be graded. So make sure you get that one done as soon as you can. And again, let me know if you have questions. Talk to you soon.